Hi, this is Mrs. Vrobel. This is part 4 of matter, properties, and changes. So in the previous video we talked about physical properties and physical changes. So we talked about density, we talked about melting point, then we talked about changing from one phase to another and the different classifications for each type of change. So today we're going to talk about chemical change. And notice that when we're looking at chemical change, we're looking at something different. We're not looking at the properties of the matter. We're looking at the loss of identity or change in composition. Now, you have to be careful when you're looking at chemical reactions because sometimes you may see what you think is evolution of gas. Now, I'm drinking my favorite beverage that I like, seltzer water, and there's gas in this liquid. However, this is not a chemical change. So you have to be careful. The other thing too is when you're looking at evolution of a gas and you see formation of bubbles, it is not boiling. You have to be careful. So occasionally you will heat up a substance or a group of materials and what you're actually seeing is boiling. Now I'll give you an instance where you will see an evolution of gas. So here I have vinegar. Whew, kind of stinky, not my favorite smell. And I'm going to add good old Arm & Hammer. So what's going to happen when I add baking soda to vinegar? Okay, I should see evolution of a gas, and I do. So you'll see formation of bubbles, you'll see fizzing. You could see a distinct odor. Remember, when you're looking at odor, you want to waft. So you want to bring the air towards your nose. You don't want to stick it directly under your nostrils. Now, the other example of chemical change would be formation of a precipitate. So when you're looking at precipitate, you're essentially looking for formation of a solid. And it could be colorful, it could not be. You'd be surprised, a lot of compounds tend to be white. You're lucky if it has color. You'll have large amounts of energy released or absorbed, and a great example of this is something that you do in your kitchen, essentially formation of a flame. And then lastly, you'll see a color change. And if you look in your kitchen, there's great examples of color changes. Most people, when they buy bananas, they tend to be green, and then as they sit in the kitchen and they ripen, they become yellow. So that's an example of a color change. Okay, so here we go. Chemical properties of substances. So when you see a change in the identity or composition of the substance, you know that you're undergoing a chemical change. So in this slide, we essentially have sodium metal. And notice that the sodium metal is shiny. So a lot of metals tend to be very metallic looking. Then we have chlorine gas. Chlorine gas, notice it's a yellow color. Oh, and by the way, it's diatomic. It's a diatomic molecule. And when you combine these two, and it's a very vigorous reaction, by the way, you get a white solid. You have an alternating pattern of sodium and chlorine ions. And we'll talk more about that when we talk about ionic compounds. Okay, so here's some more examples of the difference between chemical and physical changes. And this is something that you see all the time. You see rusting of a metal. So you go from a shiny color to a dull color. I have a piece of jewelry that if you look on the inside of the jewelry, it's nice and shiny, but if you look on the outside, it's kind of dull. It's got an oxidative coating. And I have a cleaning cloth that I use to remove the dull oxidative coating to give me more shine to my jewelry. So please remember, boiling of water is not a chemical change because you're going from one phase to another. Burning of sulfur in air is a chemical change. So anytime you have any kind of combustion or burning, you're going to have a chemical change. Boiling of an egg. So if you essentially take a raw egg, put it in boiling water, you're changing the structure of the protein of the egg, and that's essentially a chemical change. Anytime you drive somewhere, you're combusting gasoline, so that's a chemical change. Eating. So when you eat your lunch or breakfast, you're essentially digesting that food, and that food is being transferred into energy, so it has a release of heat and energy. That's why you tend to be warmer after you eat. That is a chemical change. If you are a carpenter, if you like to build things, whenever you're breaking a large piece of wood down to something smaller, notice it's a physical change. You're just physically altering the size of the material. You're not changing the composition of the wood. However, if you are having a bonfire outside, okay, anytime you're combusting something, you're undergoing a chemical change. And then lastly, glass blowing. So if you're looking at, I don't know, if you want to make something in the lab using glass, you're just undergoing a physical change. You're altering the shape of the material. You're not altering the composition of the material. Okay, let's just talk about the difference between physical and chemical properties of copper. So I have a couple pieces of copper here. Actually, I have more than a couple. But notice it's reddish brown, it's shiny, it can be shaped into sheets. This is malleable. It can be drawn into wires. This is ductile. It's a good conductor of heat. Oops, sorry, I went too far. It has a melting point, a boiling point. Notice that the melting point is very high. So remember we talked about solids, they have a high level of attraction to keep those molecules in place. That's why it has a very high melting point. Okay, and then for chemical, notice we have a color change. We're going to a green color when you have like statues or outdoor copper ornamental plates. You're going essentially from this shiny brown color to a green color. This is a lab that I hope we get to do, but I don't remember if we decided to do it or not. But you can get some really beautiful colors from copper, especially when you mix it with other chemicals. Okay, here we go. So this is a little bit different from what we've talked about up to this point. This is something that you've seen before. There's no such thing as a free lunch in the universe. So mass is neither created nor destroyed. That means that you can't get something from nothing. So if someone's telling you that they've created a miracle engine, I would be dubious. I would not accept that. If you talk to engineers, engines notoriously lose effectiveness, and they only put out a percentage of what they actually take in. So you're going to notice that conservation of mass, we're talking about not losing that mass. So what does that mean for chemistry? That means that the mass of the reactants always have to equal the mass of the products. This is a given throughout all of chemistry. You may notice, though, what you started out with, you don't get 100% of product. And the reason why is you're losing it through transfer of material. You may spill things. You may have loss of material because it went into the air. So there's a lot of different things that go on that don't give you 100%. Okay, this is the last calculation that we have to do within this chapter, and this is law of definite proportions. So what does this mean? Well, this essentially means that a compound is always composed of the same elements and in the same proportion, okay? So if I have a bottle of water, okay, there's going to be 2 hydrogen for every oxygen, no matter how much water I have. So that means for water, and it could be water here, it could be water in California, it could be here, water in Australia. Each sample of water has the same proportion of hydrogen to oxygen. And notice that it's the ratio of mass of one element to another. And it's just a real simple calculation that you have to do. So each element to the total mass. So you take the mass of the individual element and you divide it by the total mass of the compound. And notice that you multiply it by 100, and we'll do a couple examples of that. Okay, so water is 88.9% by mass oxygen and 11.1. Now, even though there's 2 hydrogens, those 2 hydrogens are very small in mass. Oxygen actually has a greater mass than than hydrogen. Okay, here we have rust, and rust contains 70% iron and 30% oxygen. So notice that iron is very large compared to oxygen, and that makes sense because it's further on in the periodic table. Okay, here we go. So this is our first calculation. So we have 84 grams of copper and 16 grams of oxygen, and they want to know what is the mass percent of each component. So what we're essentially going to do is we're going to add up the 2 of them. So 84.0, and yes, we're paying attention to sig figs, plus 16.0 grams equals 100. And then after you've calculated the total mass of each, you're essentially just going to take it, divide it by 100, and multiply it by 100. Okay, so the first percentage is essentially 84. And then the second percentage will be 16, because when you take 16 divided by 100 times 100, that gives you 16%. Another shortcut would be just to take 100 minus 84, and that'll give you the same value. Okay, and I'll let you do number 4. So go ahead and do number 4 on your own and see what happens. Okay, this is the last section. This is separating mixtures. Now notice that filtration, this is something that you'll probably be more familiar with in the lab, because you're separating a solid from a liquid with a barrier. Okay, so in the lab you're going to find that you have a solid suspended in a liquid and you want to remove the liquid and just be left with the solid. You're essentially taking filter paper and putting it in a funnel, and then you're going to remove the water and keep the solid. Distillation, so this is something that is more appropriate for advanced techniques. You're essentially boiling a solution, and you need to have a still, and the higher boiling material tends to be left behind while the lower boiling material gets condensed and removed. And when you drink or use distilled water, that's essentially what they've done, is they've removed the lower boiling point materials and you're left with just water. Crystallization, you may be doing that in one of your chemistry labs. and essentially you're just waiting for the solid to come out of solution and you're left with a liquid. And then lastly, sublimation. This is definitely an advanced technique. So you're essentially taking a solid and making it into a gas, and whatever you want is left behind, and whatever you don't want is separated out from the combination. Okay, so this last section here, we're talking about separating out using chemical means, but notice that the elements can never be separated. So there's no way that you can make the elements smaller by chemical means. However, you can use compounds and you can break them into components by chemistry. So here on the right we have a battery, and the battery is actually connected to a couple catalysts that happen to be platinum, and we're taking acidified water and we're essentially separating it out into oxygen and hydrogen. By the way, these are diatomics. So if you look at the last section of this, we have matter at the top. Oops, sorry about that. So matter at the top, and then you have two types of situations here. So you have either mixtures or you have pure substances. Now please notice that the only way that you can separate them out is through physical changes. But however, under mixtures we have what we call heterogeneous. So remember, they're not the same throughout. If you take a cross section, you're not going to see a uniform substance. You could have a homogeneous mixture. Remember that tends to be solutions. It has to be the same throughout. If you take a cross section, you're not going to see anything different. And then on the right here, for pure substances, okay, we could have elements. So elements would be by themselves. There's nothing else but the element. It could be a diatomic molecule, or it could be an atom bonded to itself. Lastly, there's compounds. So compounds would be something like what we talked about the other video. We talked about salt, we talked about sugar. I used baking soda today. So those are examples of pure substances that are compounds.